In this video, we're going to talk about how to determine the derivatives of exponential functions. In a previous video, we proved that the derivative of ln x with respect to x is 1 over x, the derivative of e to the x with respect to x is e to the x, and the derivative of b to the x with respect to x is b to the x times the natural logarithm of b. Now, putting the last two rules together with the chain rule, we get this rule. The derivative of b to the f of x with respect to x is b to the f of x times the natural logarithm of b times f prime at x. Okay, well, to put that more simply, we can say that when given an exponential function, we can determine its derivative by this rule. What you do is restate the function. So if I want the derivative of b to the f of x, what I do is I restate the function, b to the f of x, multiply by the natural logarithm of the base, and the derivative of the exponent. The exponent is f of x, so we multiply by f prime of x. If you can remember that rule, that's going to get you through a lot. And this, of course, is assuming that x is in the exponent but not the base. We'll explore later what to do if f of x is in the, if x is in the exponent and the base. For instance, if the function is x to the exponent x. We'll talk about that later. But for now, we're talking about functions where there's no x in the base, but there is in the exponent. All right, so let's do some examples. Let's determine the derivative of the following. E to the x squared minus x. This is an exponential function. We have x is in the exponents, but not in the base. So what we do is, to find the derivative, simply repeat what we were given. Repeat it. Then do the natural logarithm of the base, which is ln of e. Then do the derivative of the exponent, which is 2x minus 1. Well, the ln of e is just 1. So what we have is e to the x squared minus x times 2x minus 1, or in other words, 2x minus 1 times e to the x squared minus x. This last line is optional. What if we have f of x equals x squared e to the x? Well, this is an example of a product rule. We have x squared and we have e to the x. So to find the derivative, we do the derivative of the first function, which is 2x, times the second, e to the x, plus the first, which is x squared, times derivative of the second. The derivative of e to the x is e to the x. So we have 2x e to the x plus x squared e to the x. We can common factor out e to the x, and inside the bracket we'll have 2x plus x squared. All right, what if we want to know the equation of a tangent line? So let's say we want to know the equation of the line tangent to this function where x is 1. Well, what we're going to do is figure out the derivative of this function. We'll use the quotient rule. So what we'll do is we'll say the denominator times derivative of the numerator. The derivative of e to the x is e to the x, minus the numerator times derivative of the denominator, all over the denominator squared. Well, we want to know the slope. We now know the derivative. We want to know the value of the slope where x equals 1. So we plug an x value of 1 in here. And we get 1 squared e to the 1, which is e. And we get e to the 1 times 2, which is 2e. And the denominator is 1. E minus 2e over 1 is just negative e. Now, since y equals mx plus b, and we know the derivative is equal to negative e, we can say y equals negative ex plus b. At x equals 1, we should now know what the point is. We have the slope, and so we have this much of the equation, but we need to know a point that it goes through. Well, at x equals 1, let's figure out what y equals. E to the 1 over 1 squared. That's equal to e. So we have this equation of the line, and it's going through the point 1e. We substitute an x value of 1, a y value of e. We get e is equal to negative e times 1 plus b. Adding e to both sides, 2e is equal to b. And so what we can do here is we can say y is equal to negative ex plus 2e. That's the equation of the tangent line. Now let's do some where the base isn't e. Let's get the derivatives of the following. f of x equals 5 to the x. The derivative is restate the function, then do the ln of the base and the derivative of the exponent. The derivative of x is just 1. So what we have is 5 to the x times the ln of 5. What if the original function is 5 to the 3x minus 2? Well, to get the derivative, we repeat the function, just like it is. Then we do the natural logarithm of the base, and we do the derivative of the exponent. So this is like saying 3 ln 5 times 5 to the 3x minus 2. Now let's do a couple of word problems. First, on January 1st, 1850, the population of Gold Rush Town was 50,000. The size of the population since then can be modeled by this function, where t is the number of years since January 1st of 1850. We want to know the population of Gold Rush Town on January 1st, 1900. Well, this is fairly straightforward. That's 50 years later, so t is equal to 50. We plug that in. 50,000 times 0.98 to the exponent 50 is approximately 18,208. So on January 1st, 1900, the population was approximately 18,208. But now we want to know at what rate was the population changing at that time. We know the population is going down, but by how much? Well, the original function, p is measured in people, and t is measured in years. So our units is going to be people per year. Well, we have our original equation. Let's find the derivative. Well, to find the derivative, it's just the original function, just like it is, times the natural logarithm of the base, times the derivative of the exponent. When we plug in a value of 50, we get the ln of 0.98 times 50,000 to the exponent times 50,000 times 0.98 to the exponent 50. And the answer is negative 368. So what that means is the population is decreasing at a rate of approximately 368 people per year on that date, January 1st, 1900. All right, well, what if we have a radioactive substance? We like to do this in exponential functions chapters. So we have a radioactive substance decaying exponentially. The percent of the material left after t years is given by this equation. Well, we want to know what's the half-life. Well, the half-life means when is half of the substance remaining. 100% is there at first, so we're going to let p of t equal 50. And then we're going to solve for t. Divide both sides by 100. This becomes 0.5 equals 1.015 to the exponent negative t. And then that means that negative t is the log base 1.015 of 0.5. Or some people like to put it in their calculator by saying negative t is the log of 0.5 over the log of 1.015. Either way you do it, negative t comes out to negative 46.6, which means t is approximately 46.6, which means the half-life is approximately 46.6 years. Last part of the question says, okay, well, how fast is the substance decaying at that point, at that time? So let's find the derivative. This is a rate question, so we get our derivative. This is the original equation. To find the derivative, we just repeat the expression, then do the natural logarithm of the base, and the derivative of the exponent. At 46.6 years, we plug in 46.6 for t, and we get negative 0.74. Well, remember, p is expressed in percent, where 100 is 100% of what you were originally given. So p is expressed in percent of the original, and t is expressed in years. So we're decaying at a rate of 0.74% of the original per year.